Good evening, everyone. Today, my teammates and I are going to discuss mathematics. It is a field of study that discovers and organizes methods, theories, and theorems that are developed and proved for the needs of empirical sciences and mathematics itself. There are many areas of mathematics, which include number theory, algebra, geometry, analysis, and set theory used as foundation for all mathematics. Mathematics involves the description and manipulation of abstract objects that consist of either abstractions from nature or uh, in modern mathematics, purely abstract entities that are stipulated to have certain properties called axioms. Mathematics uses pure reason to prove properties of objects. Uh, a proof consisting of succession of applications of deductive rules to already satisfied established results. These results include previously proven theorems, axioms, and some basic properties that are considered true starting points of the theory under consideration. Mathematics is essential in the natural sciences, engineering, medicine, finance, computer science, and social sciences. Although mathematics is extensively used for modeling phenomena, the fundamental truths of mathematics are independent of any scientific experimentation. Some areas of mathematics, such as statistics, game theory, are developed in close correlation with their applications and are often grouped under applied mathematics. Other areas are developed independently from any application, but often later find practical applications. Historically, the concept of a proof and its associated mathematical rigor first appeared in Greek mathematics, most notably in Euclid's Elements. Since its beginning, mathematics was primarily divided into geometry and arithmetics until the 16th and 17th centuries, when algebra and infinitesimal calculus were introduced as new fields. Since then, the interaction between mathematical innovations and scientific discoveries has led to correlated increase in development of both. At the end of 19th century, the foundational crisis of mathematics led to the systematization of the axiomatic method, which heralded a dramatic increase in the number of mathematical areas and the fields of application. The contemporary of mathematics subject classification lists more than 60 first level areas of mathematics. Now I'm going to discuss about areas of mathematics. Before Renaissance, mathematics was divided into two main areas, arithmetic in geometry. Some types of pseudoscience, such as numerology and astrology, were not then clearly distinguished from mathematics. During the Renaissance, two more areas appeared, mathematical notation with geometry and calculus, consisting of two subfields, differential calculus and integral calculus, is the study of continuous functions, which model the typically nonlinear relationships between varying quantities as represented by variables. This division into four main areas, arithmetic, geometry, algebra, and calculus, endured until the era of 19th century. Areas such as celestial mechanics and solid mechanics were then studied by mathematicians, but now considered as belonging to physics. The subject of combinometrics has been studied for much of a recorded history, yet did not become a separate branch of mathematics until the 17th century. At the end of 19th century, the foundational crisis in mathematics and the resulting systemization of the axiomatic method led to an explosion of new areas of mathematics. The 2020 mathematics subject classification contains no less than 63 first level areas. Some of these areas compared to older division as true regarding number theory and geometry. Several other first level areas have geometry in their names or otherwise commonly considered part of geometry. Algebra and calculus do not appear as first level areas but are respectively split into several first level areas. Other first level areas emerged during the 20th century or had previously been considered as mathematicians such as mathematical logic and foundations. Now my friend going to discuss about number theory.
Now I'm going to speak about number theory. I'm Dinesh. Number theory began with the manipulation of numbers, that is, natural numbers, and later got expanded to integers and rational numbers. Number theory was once called arithmetic, but nowadays this term is mostly used for numerical calculations. Number theory dates back to ancient Babylon and probably China. Two prominent early number theorists were Euclid of ancient Greece and Diophantus of Alexandria. The modern study of number theory in its abstract form is largely attributed to Pierre de Fermat and Leonhard Euler. The field came to full fruition with the contributions of Adrian Marie Legendre, and Carl Friedrich Gauss. Many easily stated number problems have solutions that require sophisticated methods, often from across mathematics. A prominent example is Fermat's last theorem. This conjecture was stated in 1637 by Pierre de Fermat, but it was proven only in 1994 by Andre Willis, who used tools including scheme theory from algebraic geometry, category theory, and homological algebra. Another example is Goldbach's conjecture, which asserts that every even integer greater than 2 is the sum of prime numbers. Stated in 1742 by Christian Goldbach, it remains unproven despite considerable effort. Number theory includes several subareas, including analytical number theory, algebraic number theory, geometry of numbers, Diophantine equations, and transcendence theory. Now I'm going to speak about calculus. Calculus, formerly called infinitesimal calculus, was introduced independently and simultaneously by 17th century mathematicians Newton and Leibniz. It is fundamentally the study of the relationship of variables that depend on each other. Calculus was expanded in the 18th century by Euler with the introduction of the concept of a function and many other results. Presently, calculus refers mainly to the elementary part of this theory, and analysis is commonly used for advanced parts. Analysis is further subdivided into real analysis, where variables represent real numbers, and complex analysis, where variables represent complex numbers. Analysis includes many subareas shared by other areas of mathematics, which include multivariable calculus, functional analysis, integration, measure theory, potential theory, ordinary, ordinary differential equations, and partial differential equations. Now I am going to speak about discrete mathematics. Discrete mathematics, broadly speaking, is the study of individual countable mathematical objects. An example is the set of all integers. Because the objects of study here are discrete, the methods of calculus and mathematical analysis do not directly apply. Algorithms, especially their implementation and computational complexity, play a major role in discrete mathematics. The four color theorem and optimal sphere packing were two major problems of discrete mathematics solved in the second phase of the 20th century. The P versus NP problem, which remains open to this day, is also important for discrete mathematics, since its solution would potentially impact a large number of computationally difficult problems. Discrete mathematics include combinatorics, the art of enumerating mathematical objects, graph theory and hypergraph graphs, coding theory, including error correction codes, and a part of cryptography, matter theory, discrete geometry, discrete probability distributions, game theory. Now, my friend gonna continue about the remaining topic.
Hi everyone, this is Kishan. Now I am going to discuss about algebra. Algebra is the art of manipulating equations and formulas. Diophantus and Al-Khwarizmi were the two main precursors of algebra. Diophantus solved some equations involving unknown natural numbers by deducing new relations until he obtained the solution. Khwarizmi introduced systematic methods for transforming equations, such as moving a term from one side of an equation into the other side. The term algebra is derived from the Arabic word al-jabr, meaning the reunion of broken parts. Algebra became an area in its own right only with Francois, who introduced the use of variables for representing unknown or unspecified numbers. Variables allowed mathematicians to describe the operations that have to be done on the numbers representing using mathematical formulas. Until the 19th century, algebra consisted mainly of the study of linear equations and polynomial equations in a single unknown, which were called algebraic equations. During the 19th century, mathematicians began to use variables to represent things other than numbers, on which generalizations of arithmetic operations are often valid. The concept of algebraic structure addresses this. Consists of a set, whole elements are unspecified, of operations acting on the element of the set, and rules these operations must follow. The scope of algebra thus grew to include the study of algebraic structures. The object of algebra was called modern algebra or abstract algebra, as established by the influence and works of Emmy Noether. Some types of algebraic structures have useful and often fundamental properties in many areas of mathematics. Their study became autonomous parts of algebra and include group theory, field theory, vector space, ring theory, commutative algebra, homological algebra, and Boolean algebra. The study of types of algebraic structures as mathematical objects is the purpose of universal algebra and category theory. The latter applies to every mathematical structures. At its origin, it was introduced. Together, the homological algebra for allowing the algebraic study of non-algebraic objects such as topological spaces. This particular area of applications is called algebraic topology. Now, calculus and analysis are calculus formerly called in infinitesimal calculus was introduced independently and simultaneously by the 17th century mathematics, Newton and Leibniz. It is fundamentally the study of relationship of variables that depend on each other. Calculus was expanded in the 18th century by Euler with the introduction of the concept of a function and many other results. Present calculus refers mainly to the elementary part of this theory and analysis is commonly used for advanced parts. Now, my friend discussed more topics. Thank you.
I'm going to talk about geometry. Geometry is one of the oldest branches of mathematics. It started with empirical recipes concerning shapes such as lines, angles, and circles, which were developed mainly for the needs of architecture and surveying, but has since blossomed out into many other subfields. A fundamental innovation was the ancient Greeks' introduction of the concept of proofs, which require that every assertion must be proved. For example, it is not sufficient to verify by measurement that, like, let's say two lengths are equal, but their equality must be proven via reasoning from previously accepted results and a few basic statements. The basic statements are not subject to proof because they are self evident or are part of the definition of the subject of study. This principle, um, foundational for all mathematics, was first elaborated for geometry and was systematized by Euclid around 300 BC in his books. The resulting Euclidean geometry is a study of shapes and their arrangements constructed from lines, planes, and circles in the Euclidean plane and the three dimensional Euclidean space. Euclidean geometry was developed without change of methods or scope until the 17th century, when Rain introduced that what is now called Cartesian coordinates. This constituted a major change of paradigm. Instead of defining real numbers as lengths of line segments, it allowed the representation of points using their coordinates such as numbers. Algebra can thus be used to solve geometrical problems, and also geometry was split into two new subfields. One is synthetic geometry, which was purely about the geometrical methods, and the next one is analytic geometry, which uses coordinates systematically. Analytic geometry allows the study of curves unrelated to circles and lines. Such curves can be defined as the graph of functions, the study of which led to differential geometry. They can also be defined as implicit equations, often polynomial equations. Analytic geometry also makes it possible to consider Euclidean shapes of higher than three dimensions. In the 19th century, mathematicians discovered non Euclidean geometries which do not follow the parallel postulate. By questioning that postulate's truth, this discovery has been viewed as joining Russell's paradox in revealing the foundational crisis of mathematics. This aspect of the crisis was solved by systematizing the axiomatic methods and adopting that the truth of the chosen axioms is not a mathematical problem. In turn, the axiomatic methods allow for the study of various geometries obtained either by changing the axioms or by considering properties that do not change under specific transformations of the shape. Today's subareas of geometry include projective geometry, introduced in the 16th century by Girard, extends Euclidean geometry by adding points at infinity at which parallel lines intersect. This simplifies that many aspects of classical geometry by unifying the treatment for intersecting and parallel lines. And the next one is affine geometry, the study of properties relative to parallelism and independent from the concept of length. Differential geometry is the study of curves, surfaces, and their generalizations, which are defined using differentiable functions. And also, there are some other topics like manifold theory, algebraic geometry, and also about the polynomials, topology, and then discrete geometry, and convex geometry. Yeah, so these are the topics which we want to discuss today. Thank you.